Hello everyone, I once again welcome you all to MSP lecture series on interpretive spectroscopy. This is the 10th lecture in the series. In my previous lecture, I was discussing about 13C NMR spectra and related aspects and how one can compare the data obtained from 1H NMR with 13C and how to simplify 13C if you have large number of hydrogen atoms. We use decoupling system. So, let me continue from where I had stopped. Just if you recall the spectra I showed in my last lecture, you can see here 13C NMR spectra is recorded both with coupling and without coupling. This is without coupling. I would say 13C like this. Once if we write in the flower bracket any nuclei next to the one we are looking into, that indicates any signal due to this one is decoupled. And this one is coupled one. So, in the coupled one you anticipate interaction of carbon with adjacent hydrogen atoms. For example, here when carbon interacts with 3, we should get a quadret we are seeing here, and then again this one is also, this carbon also coupled with these 3 and it will show another quadret here, and then this one methylene is split by 2 hydrogen atoms. So, we are getting 3 here. If you are not understanding how this is giving, for example, here we can use simply 2Ni plus 1 rule here. So, here carbon is attached to 3 hydrogen atoms, so 2 into 3 and its spin is half. So, it gives 4 lines. Okay, this is how you can calculate. So, we are seeing 4 lines, and in case of this one also we are seeing 4 lines, whereas in case of methylene we are seeing 3 lines. And of course, here what happens, we have 1, 2, 3, 4 different type of carbon nuclei are there. As a result, we are seeing 1, 2, 3, 4. So, this is much better, this is simplified one. In case if we want to have further information to see how it is interacting, and one can always record coupled spectrum, whether it is 13C or whether it is phosphorus NMR or it is fluorine NMR, we can always record coupled as well as decoupled ones. One example is shown here. We have at para position, we have fluoro group is there. So, parafluorotoluene it is, and if you just look into this molecule here, this one and this one are identical, and this one and this one are identical. This is unique, this is unique, and this is unique. So, that means 1, 2, 3, 4, 5 peaks should be there. So, we have here 1, 2, 3, 4, 5 signals are there. And then it is a simple, but fluorine is also there. It is likely that fluorine can couple strongly with this carbon atom here, this carbon atom here, and then it can weakly couple with these 2 as well, but here it may not show any coupling because 1, 2, 3 bond coupling. Let me see how it looks like. Yes, you can see here the one with larger coupling, what we see here, this is due to this 1 bond carbon fluorine coupling, whereas these 2 will be coupled with this one, that is little long range, you can see here, and then these 2 are coupled weakly, and that can be seen here, and then this does not show any coupling, it comes here, and this one is coming here. So, that means basically coupling also helps in understanding the position of signals in a given spectrum. Now, I am presenting another interesting molecule here. You can see dichloro-trimethyl methane here. And if we look into 13C NMR spectrum, we are expecting 2 signals here. One is for this methane carbon, and then other one is methyl group present on silicon. So, here, and simply by looking into the coupled spectrum, the C13C, this one will couple with H2, show a doublet, and then this carbon here, all 3 are equivalent. As a result, we can anticipate only 1 carbon signal in each carbon signal. So, you can see the coupling with 3 protons. So, it will appear as a quadret. But if we look into the fine spectrum of this one after expanding, this quadret on expanding, each line would be consists of a septet, and each septet is again, each line is a doublet. And similarly, if we look into the signals here in the doublet, each signal consists of 10 lines here. So it is interesting to analyze how these 10 lines are coming here and how each one is a septet of doublets, how it is appearing here. You can see here, first I have expanded version of this one I am showing here, in why each line is showing 10 lines here. And of course, if I just write the structure here, so first this carbon will couple with hydrogen to give a doublet, certain larger coupling one can anticipate. Now this carbon is coupled with 1, 2, 3 bond coupling, 3 bond coupling with 9 hydrogen atoms are there, 9 hydrogen atoms are there. If I just again use this 2Ni plus 1 rule here, 2 into we have 9, so 10 lines, you can expect 10 lines, that is what we are seeing here. So that means you can also see 1J CH coupling plus we are seeing 1, 2, 3, 3J CH coupling. So first it will appear as a doublet and each line will be split into so each one, so you will see 10 lines here. You can see here 10 lines are here. So this is how you can understand the complex pattern appears, although it appears like a doublet. After expanding, you can see the fine splitting here showing both 1J as well as 3J coupling with hydrogen atom. Now let us look into the quadret here. Now in the quadret, it is very interesting. Let us just look into trimethylsilyl group here. So once when we are considering one of the signal here 13C, others may be 12, not necessarily they will be 13. In this case what happens, first it will split with this one into a quadret, and then since now these two are non-equivalent, they can split, protons will split this one into each one into a septet. The same thing happens in all cases. After that one, you can see again 3J coupling. This one will be coupled with this hydrogen. 1, 1, 2, 3 coupling. So 3J coupling is also anticipated. Only one is there. Each one will be split into a doublet. So you can see now this is how a quadret, a simple quadret after expansion, it appears like septet of doublets. You can see here, I have shown here a quadret. Each quadret is split into 7 lines, and then each line in the septet is further split into a doublet because of 3J CH coupling, and then eventually if you just look into it, it appears like this. It is very simple to understand if we expand and get the fine spectrum. And let us look into another example here, and in this molecule all are very different. As a result, we can anticipate 6 carbon atoms in the aromatic region, and all the 6 carbon atoms are shown here. 1 is here, 2 is here, and 3, 4, 5, 6 are there. And now if you just look into one is split into a doublet because this one is about 1, 2 bond coupling. This is due to 2 bond carbon fluorine coupling, and then 2 is directly attached to fluorine. So you can anticipate larger coupling. As a result, it is split further. This is 1J CF, whereas this portion is 2J CF. And in the same way, you can see C5 is further, the coupling is very small because 1, 2, 3, 4 bond coupling is there. So you can see here 4J CF, and then 4 will be little here, 1, 2, 3, so 3 bond coupling will be there, and 3 will be 2J coupling, and then 6 doesn't show any coupling as it is very far. That means if we have another NMR active nuclei is there, assignment becomes much more simplified just by looking into the magnitude and how farther this nuclei is from the nuclei under consideration. We should be able to elucidate the structure very easily. This is how one can use other NMR active nuclei present in a molecule for better interpretation. Okay, now let us look into symmetrically substituted compound here. Here we have, if you consider from here, we have 1,3 position, we have substitution is there. So now these two are identical and these two are identical and this is different and this is different. That means one can anticipate 4 signals for this difluorobenzene, meta-difluorobenzene. You can see here we have 1, 2, 3, 4, 5 are there, and 4 and 6 appear together. The reason is although we say these two are chemically equivalent and their interaction with fluorine is very different. For example, this one has a 2-bond coupling with fluorine, they are identical. We have C2 axis of rotation is there, but still 6 interaction with fluorine, F1 is different from F2, and similarly interaction of 4 with F1 is different from F2. As a result, we get a different pattern here, whereas C2 will show very nicely triplet, and then C5 will also show a triplet here, and then C1 and C1 will show a doublet, and C3 will also a doublet of almost same coupling value. Whereas here this portion we have a different spin system is there, it appears something like this here. So this we call it as virtual coupling. So now let us try to analyze 1H NMR data for better understanding again. The presence of a paramagnetic center with 1 or more unpaired electrons in a compound has significance on 1H NMR spectrum chemical shifts. First, the local magnetic field at each of the 1H nucleus is affected. When NMR active nucleus is placed in an external magnetic field, the energy difference between nuclear spin states arises due to the interaction of the magnetic fields of the spinning nuclei with the applied field. However, the local field experienced by the nuclei is not the same as the applied field, because the electron pairs in the vicinity of the hydrogen nucleus generate small local magnetic fields. And these magnetic fields, as I had mentioned earlier, they can align with the magnetic field or they can oppose the magnetic field. Depending upon their alignment, we will see some sort of shifts and also the further splitting. The local magnetic field is the sum of the applied field and all the smaller fields. The later depend on the chemical environment of the hydrogen nucleus. This is very, very important. So all these chemical shifts essentially depend on chemical environment of the hydrogen nucleus. Typically, the difference in local magnetic fields for protons in the different environments are small, and as a consequence, the chemical shift range over which the 1H NMR occurs is not large. So whatever the chemical shift difference that we come across, that is considerably low compared to other nuclei. As a result, we have a small spectral range of 1 to 10 ppm in case of 1H NMR. In a paramagnetic compound, there is an additional factor. A large local magnetic field is arising from the unpaired electrons or electrons on the paramagnetic center. So when we have paramagnetic center, what happens? Because it generates again another magnetic field that can again oppose or align with the magnetic field, and hence we will see unusual shifts in such molecules. And this happens especially in case of metal complexes where we have lot of unpaired electrons are there, and if it is paramagnetic, and if it is diamagnetic, it is not an issue. If the complex is paramagnetic due to unpaired electrons, and if we have some hydrogen atoms attached directly to metal, we can see enormous shift will be there to a shielded region. This contributes to the energy difference between nuclear spin states, and as a consequence, the chemical shift range for the 1H NMR signals is much larger than in a diamagnetic compound. It can go up to -15, -20, or it can go up to even +60 sometime. The second effect that is observed in 1H NMR spectra of paramagnetic compounds is broadening of the signals. This effect has its origins in a significant shortening of the excited state lifetime. The relaxation time is very short. That means we have to look into relaxation times. We have spin relaxation, spin lattice relaxation. What would happen to this relaxation if we have paramagnetic species. Anyway, so since I am more focusing on interpretation, I am not going to the details of those things. If you want to look into the details of those aspects, I am sure there are better courses are there where theoretical aspects are discussed in detail. Probably you can refer to those, or you can read appropriate book for that one. So in some cases, the broadening is so great that no well resolved signals are observed. In some cases, probably we may miserably fail to record a spectrum because of paramagnetic species present in the molecule. So let us consider a simple paramagnetic species, trisphenanthroline cobalt 2 plus complex here. Cobalt 2 can have 1 or 3 unpaired electrons in an octahedral complex depending upon the ligand field strength. So if you see, this is D7 system, we have something like this, we can have something like this, or we can also have something like this if it is low field or low spin. So we can have either 1 or 3 unpaired electrons. So it is very interesting to examine 1H NMR spectrum of this complex trisphenanthroline. There are 4 different aromatic proton environments are there in this one, and the chemical shifts of the signals assigned to these 1H nuclei fall in the range of plus 110 to 15. So you can see, otherwise in most of the organic molecules the chemical shifts are confined to 10 ppm, 1 to 10, whereas in this case it can go to as low as 110 to 15, or in some cases it can also go to minus 15 or minus 20. So here what are those 4 signals we are getting due to which protons? We can see here. I have labeled one phenanthroline molecule here, others are also identical, so you can label them as 1, 2, 3 and then 4 here, and similarly 1, 2, 3 and 4 here. So 4 signals we are seeing in this 110 to 15 range. I would come back again to 13C and 1H wherever we come across spectrum, or at the end I will be discussing problems where I would take NMR spectra along with IR and UV data to elucidate the structure. So now let us focus our attention to phosphorus 31P NMR. And phosphorus 31P NMR is very similar to 1H NMR. The concept of 31P NMR is very similar to proton NMR. Here also we have natural abundance of 31P 100% and spin I equals half, nuclear spin I equals half. The 31P nucleus is useful in NMR spectroscopy due to its relatively high gyromagnetic ratio of 17.235 megahertz per Tesla. For 1H, if you recall, it is 42.576 megahertz per Tesla, and in case of 13C it is 1/4 of 1H, so it is around 10.705 megahertz per Tesla. The spectral interpretation is much easier, and also it is very similar to 1H NMR. 31P NMR is an excellent technique for studying phosphorus containing compounds such as organic compounds, coordination complexes and molecules of biological importance, and also in materials where we have phosphorus, and also especially this is very useful in understanding the intermediates in homogeneous catalysis if you have phosphines as ligands in those metal mediated catalytic reactions. And now let us try to look into the differences between 1H and 31P NMR. And 1H NMR spectra is referenced to TMS, tetramethylsilane, whereas in case of 31P NMR we are using 85% phosphoric acid, and we are considering its chemical shift as 0, and it is used as an external standard because we cannot add 85% H3SO4 directly to the solution containing phosphorus compounds, as it can react with it. It is used as an external standard. Another standard is trimethyl phosphate or trimethoxyphosphine is also used as a standard, and unlike phosphoric acid, it is independent of concentration or pH, so we can use it without any problem. And with respect to phosphoric acid, the shift of trimethyl phosphate is around 140 ppm. Similar to 1H NMR, positive chemical shifts corresponds to downfield shift. From the standard, chemical shifts in 31P NMR commonly depend on the concentration of the sample, the solvent used, and the presence of other compounds. This is because the external standard does not take into account the bulk properties of the sample. As a result, the reported chemical shifts for the same compound could vary by 1 ppm or more, especially for phosphate groups. Whenever we have a pentavalent phosphorus having P double bond O, In this case, what happens? The chemical shifts. For the same sample, if you record, and there can be some variation. It's because of homogeneity problem and other things, as I mentioned here. Since the bulk properties are not considered here, so that can show this kind of variation. 31P NMR spectra are often recorded with all proton signals decoupled, very similar to decoupling process we use in case of 13C. Here also conveniently we can use decoupling process, and we can record 1H decoupled 31P NMR. That will be very simple, and it's very simple to assign. This gives rise to single sharp signals per unique phosphorus. And herein we will consider both coupled and decoupled spectra, but very nicely we can see two phosphorus couplings up to 3, 4 or 5 bonds. They are chemically and magnetically non-equivalent. Interpretation of spectra, easy, very similar to 1H as I mentioned earlier. As in 1H NMR, phosphorus signals occur at different frequencies depending on the electron environment of each phosphorus nuclei. So let us consider some examples here. So you can see the extensive list of chemical shifts and the chemical shift range for various type of phosphorus compounds we come across. So let me elaborate on this one in my next lecture. Until then, have an excellent time reading on spectroscopy. Thank you.